we now come to the next topic of series. Infinite series are related to sequences but are not exactly coincident with the concept of sequences. Let me first make the definition before I continue with general remarks. Definition: an infinite series is a formal expression of the form summation n equal 1 to infinity bn, which we also write as b1 plus b2 plus b3 and so on. Okay, so given an infinite series, we define the partial sums Sm to be equal to b1 plus b2 plus dot 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 bm. We say the series summation n equals 1 to infinity bn converges to L, or summation n equals 1 to infinity bn equal to L if Sm converges to L. Okay, as this definition is very important, let me read it out again. An infinite series is a formal expression of the form summation n equals 1 to infinity bn, also written as b1 plus b2 plus b3 plus so on. Given an infinite series, we define the partial sums Sm to be the sum of the first m terms b1 plus b2 plus dot 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 bm. We say the series summation n equal to 1 to infinity bn converges to L, or that the series is equal to L if the sequence of partial sums Sm converges to L. So there are two remarks that I would like to make. The first one is remark associated to a series there are two sequences. One is the sequence bn, the other is the sequence Sm. Okay, and the convergence of the series is determined by this convergence of Sm, not by the convergence of bn. Okay, we will now see that if a series does converge, this sequence bn must also converge, and it must converge to 0. That mostly acts as a negative test for series converging. You can determine that a series does not converge by showing that bn does not converge to 0. But the more important sum for us is this sum Sm, the sequence of partial sums. This is the one that actually plays the central role for determining convergence. So let us see one example of a convergent series and one example of a divergent series. So example. Let's consider summation 1 by n squared n equals 1 to infinity. Okay, so it might be a good idea to write down the first few terms just to get an idea of what is happening. It's 1 plus 1 by 4 plus 1 by 9 plus 1 by 16 plus so on. Okay, now what I do is, I know that the sequence of partial sums Sm is increasing simply because the series has terms that are all non-negative. So it's nothing special about this series 1 by n squared. Any series in which you have the nth term bn to be greater than or equal to 0 always, will have this nice property that the sequence of partial sums will be increasing. Now a light bulb should flicker over your head. If a sequence is increasing, then it is convergent if and only if it is bounded above. That's the monotone convergence theorem. By the monotone convergence theorem, it is enough to show that Sm is bounded above. Then we will automatically know that it's convergent. Note, the approach I am taking will give you no idea what this sum is. We will determine what this sum is at a later time in the course. It's a very interesting sum. But the approach I am taking right now, I'm completely choosing to ignore the limit L and directly conclude that this series converges without giving us any clue as to what L is. Actually, we'll get some idea what L is if you carefully follow what I'm about to do. Now, I want to show that the partial sums are bounded. So what I want to do is, I want to bound the partial sums from the above. So what I will do is, I will start estimating the terms of the partial sums, but at each time increasing the quantity. If I increase the quantity, then what I estimate, I will get a less than inequality. So if that sounds vague, just wait a moment, you will understand what is going on. What I do is, I write this as 1 plus 1 by 2 into 2. So let me just write Sm is 1 plus 1 by 2 into 2 plus 1 by 3 into 3 plus 1 by m into m. This is the sum of the first m terms. Okay. Now, as I said, I want to make this less than something. So I want to increase each one of these quantities. Now, each one of these quantities is a quotient. To increase a quotient, the natural thing to do is to decrease the denominator. So this is less than 1 plus 1 by 2 into 1 plus 1 by 3 into 2 plus 1 by m into m minus 1. Fine. Now here is the trick. This is equal to 1 plus 1 by 1 minus half plus 1 by 2 minus 1 by 3 plus 1 by m minus 1 minus 1 by m. Okay. That this is correct is just basic arithmetic from 5th standard. Okay, how has this helped us? Well, zoom in and you will notice something happening. Tunk, tunk, tunk. Let me just write the next term so that I can tunk it. So this will be 1 by 3 minus 1 by 4 plus . Now I can tunk it, tunk, tunk. So on, you see that the second term will get cancelled with the first term of the next part, right? And this will repeat. So eventually everything up till this 1 by m minus 1 will get cancelled, right? Will get cancelled. So what you will get is Sm is less than 1 plus 1 minus 1 by m, right? Which is certainly less than 2. So conclusion is that Sm is bounded above. Okay. Hence summation 1 by n squared converges, but the limit is unknown. To us currently. Okay, so one question you might ask is, oh, this is all nice and good, but there seems to be some trickery involved in finding out that summation 1 by n squared converges, and this is about the simplest series possible. Well, one of the issues in presenting mathematics is I have a limited amount of time to convey a lot of information. Now, the first person who managed to show that this is actually a convergent series, I don't know who that person was, probably did not get it in 7 minutes, which is roughly the time it has taken for us to actually show that this is convergent. It probably took many days. That person is likely to have experimented a lot with some heuristic reasoning, like what I said. You want to make the terms less than something, so you try to increase each individual term, so you try to decrease the denominator and so on. So he must have spent a lot of time manipulating this algebraically and finally landed up with this proof. Now, if you were to ask me how exactly did he think of this particular line of approach, I don't really have an answer, because when you experiment, you don't always experiment in a perfectly logical and linear way. You try out various things and it clicks. So you must always understand that there's a bit of experimentation involved in all of this, guided by heuristics. You shouldn't be randomly combining terms and hoping that life falls into place. That's not the way life works. Okay, you'll have to plan systematically, but at the same time, you should not be so rigid. Okay, so all these remarks are just an excuse for me to give example 2, which will have similar manipulations. Example 2, let me change to blue. Summation 1 by n diverges. The series 1 by n squared converges, but the series 1 by n diverges. Well, this might be a bit shocking to you, but you can do this following experiment on a calculator or a computer and try to see what exactly happens by summing up 1 by n for the first 10,000 terms, the first 1 lakh terms, the first million terms, and so on, and you will see that it slowly increases. It diverges, but it diverges very slowly. Okay, so again by monotone convergence theorem, by convergence theorem, by the way, this should be implicit in my by the way I'm talking. If a series does not converge, we say it diverges. Let me just make that clear, because I don't think I wrote it down explicitly in the definition. Again, by monotone convergence theorem, it is enough to show that Sm is not bounded above. Then I would be done. Okay, so let's write down Sm. It will be 1 plus half plus 1 by 3 plus dot 1 by n. Right, this is what Sm is. Now what I am going to do is I am not going to consider Sm, I am going to consider S 2 power k greater than 0. If I can show that this S 2 power k, so of course I must write k in the natural numbers. That's better than writing k is greater than 0, which is ambiguous. If I can show that this S 2 power k itself is unbounded, is bounded or not bounded above, then certainly Sm is unbounded above. Okay, so what will this S 2 power k be? Well, it's just again 1 plus half plus 1 by 3 plus dot plus 1 by 2 power k. Okay, this is a bit silly. It really doesn't seem like I've done anything other than substitute m equal to 2 power k, but this is going to make a world of difference in the next step. I write this as 1 plus half plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 plus dot 1 by 2 power k minus 1 plus 1 plus 1 by 2 power k minus 1 plus 2 plus dot 1 by 2 power k. Okay, and here there are 2 power k minus 1 terms. You see what I have done? I combined 2 terms first, then I combined 4 terms, then obviously I'm going to combine 8 terms, so on, and finally I'm combining 2 power k minus 1 terms. Okay. Now check that this arithmetic works. Check that this arithmetic works. Okay, I can't just say I'm combining terms if there are not enough terms for me to combine. Okay, arithmetic works. That's just summing up a very finite set of terms of a geometric series. So 2 plus 4 plus dot 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 2 power k minus 1, you will immediately see that that's 2 power k minus 1 minus 1 or something like that, or very close to that. Or rather 1 plus 2 plus 4 plus dot 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 2 power k minus 1 will be exactly 2 power k minus 1, and there's a 1 here, so put together there are 2 power k terms. So I am accounting for every single term, and it's possible to split up this series in this way, this finite series in this way. Okay, now what is the moral of the story? I want to make this term greater than something and show that what it's greater than sort of diverges to infinity, right? So what I want to do is I want to get a greater than bound. So what I will do is I'll have to make each one of these quantities larger, right? I want to make each one of these terms smaller, not larger. That means I want to increase the denominator, and it should be fairly easy to guess the next step. It's 1 plus a half plus 1 by 4 plus 1 by 4. I'm increasing the denominators, plus 1 by 8 plus dot 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 1 by 8, 4 terms, plus dot 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 plus 1 by 2 power k plus dot 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 1 by 2 power k, 2 power k minus 1 terms. 2 power k minus 1 terms. Right? So what will this give us? This will give us 1 plus half plus 2 into 1 by 4 plus 4 into 1 by 8 plus dot 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 2 power k minus 1 into 1 by 2 power k. Right? Well, that's just going to be 1 plus half plus half plus half, so on and so forth. How many such terms? They will be k halves, k terms like this. Okay, so this will immediately give 1 plus k by 2. This will give 1 plus k by 2, which diverges to infinity. Which means the set S2k is not bounded above. So consequently, by the monotone convergence theorem, summation 1 by n diverges by monotone convergence theorem. Okay. So here we see that the behavior of summation 1 by n is quite different from behavior of summation 1 by n squared, and we are able to see the difference in the way we combine the terms and do this algebraic manipulation. Okay. Now what I will do is, in the next module I will state and prove the Cauchy condensation test that sort of takes into account these manipulations that we are doing and makes it into a general theorem. This is a course on real analysis, and you have just watched the module on definitions and examples of infinite series.